So we can definitely write this equation f naught is equal to f naught cosine 30 x hat minus f naught sine 30 y hat. Now in terms of specific numbers, cosine of 30 is about 0.866. You got 500, 500, oh, I don't know. What's that? 400 what?
433.
So 433 newtons, give or take, x hat. Now, that's minus 250 newtons, y hat. I happen to know sine of 30 is a half. Okay, so there you go, that's f naught. And then so how do I solve this problem? Bring it all together, right? So in the x direction, what we got? We've got, let me just expand this. So this is 0 equals to what? 0 is equal to the normal force minus the weight, right? Minus 250 newtons, because that's the x component, that's the y component of the pushing force, right, which is downward. And then what? On the other hand, MA is equal to, what's the x? Just 433 newtons. But M is what? M was 100 kilograms. So 100 kilograms times A is equal to 433 newtons. Therefore, the acceleration is 4.33 meters per second squared. There you go.
In a test answer, we have to give a direction to that.
Well, I said what I find the I mean, it depends on the question. I would usually have a little more words. I'd like say find the acceleration of the box along the plane. So in that case, I don't really need a vector answer. If I said it as a vector, then yes, but it kind of depends on the wording. So we do have some customs here to free you of some of the vectorness of the problem. Let's smell the roses here. One of the roses we might take a moment to smell. The normal force is in fact equal to mg plus 250 newtons. Now I can figure out the specific number here, but my larger point view, and I would emphasize this for later purposes, the normal force need not be the weight. The weight is this. This is the weight. Right? Does the weight have to be the normal force? No. This is the quintessential mistake you guys make in your current course. You gravitate towards it. You want to make this mistake. No, you don't want to make this mistake. I really shouldn't draw your attention to it. Now it's my fault that you're making the mistake. I'm sorry, but you know, I'm still going to take points. I'm sorry, is it too soon? I was going to test back out, I guess, but too early. Anyway. I have time for an inclined plane problem. Woo. So, most simple inclined plane problems I can think about would be the following. I have a frictionless incline at angle theta, and I've got a mass, m. It's actually easier if I don't put in numbers. I want you to tell me what's the acceleration down the plane. Like that. So again, this is a frictionless plane. And we're on Earth, near the surface. The force of gravity on the box is given by mg downward.
So you're asking for the acceleration parallel to the plane?
Exactly, yeah. What is the acceleration parallel to the plane? So here's how I start. What are the forces at work, right? Draw the free body diagram. So, I'll do it in your head. Of course, there's the normal force, which is which direction now? Perpendicular to the plane, right? Normal to the plane, so now it's this way. There's your F sub n. Let me erase the acceleration vector because that's not really where it's at. I mean, I want to know what that is, right? All right, it's our goal, find the acceleration down the plane. What else? What other forces? Gravity, that's it, right? At least for now. Before you know it, I'll make somebody push on it. We'll add a friction force and other junk, but for now, gravity. Which looks like these. Now, I guess you got two options. You could try to analyze this in the XY coordinate system, like just the Y this way, X this way, you know, horizontal, vertical, but that's not very natural. Problem, really you want to break things into the parallel and perpendicular directions, right? Now other people, when they teach this, they will call the X direction the parallel to the plane and the Y the perpendicular to the plane. I don't do that. I just call them parallel and perpendicular. I just think it makes for less confusion with you guys than if I relabel X and Y to mean different things. Forgive me if I have a dim view of you. I have a dim view of me too, which is I'll forget what X and Y are later. It's just easier to call it what it is, parallel and perpendicular. Actually, it's not always that easy to say, but it is what it is. So, parallel and perpendicular. Although we have symbols, parallel, perpendicular. So, if I draw a picture, let's see here. I guess the real issue, right, is the normal force. Well, that's easy enough, right? So let's see here. First of all, this will be the one we have MA, right? The A I'm looking for is the perpendicular acceleration. What's the acceleration perpendicular to the plane? What's the acceleration perpendicular to this plane? 0. It's staying along the surface of the plane, right? So over here, the perpendicular acceleration is 0, which is to say it's staying on the plane. It's not accelerating off the perpendicular direction of the plane. It's just accelerating along the plane. So in the normal direction, or the perpendicular direction, it's not accelerating. Okay, so I mean, also, this much is clear. If I take this as the positive direction, I've got S of n here, right? That's great. One thing down. Now gravity to go. But see, gravity, now, before we didn't need to break gravity into horizontal and vertical components because it was vertical, right? But now, gravity is a little bit parallel, it's a little bit perpendicular. I have to break gravity into pieces. So the way to do that, watch carefully, is just this triangle here. Right? I want to explain this once, carefully and slowly. What angle is what in the purple triangle? Can you see it?
The one by the point is
So I guess my real question is the upper angle theta or the lower angle theta? You can kind of see one of them.
Upper.
Yeah, this angle here is theta, right? Right, wrong.
Yeah.
Why is that? Geometry is a good answer. That is actually the answer. Let's see here. Suppose if I were to move, if I could think about it this way, if I move the mg down to here, and then I look at the vector like this, might be able to see it easier. This angle is complementary to theta. That makes this have to be theta since that's a right angle. And that triangle is similar to the larger purple triangle I wrote up there. Listen, how you see this is your business, but you must see this. That angle is theta, if this angle is theta. Why does that matter? It matters because if the hypotenuse is mg, the adjacent side is mg cosine theta, and the opposite side is mg sine theta. Right? Now the question is, do you want to take down the plane as positive or up the plane as positive? It's your choice. Which direction is going to be positive A? Down is going to be positive? All right, down is positive, then I write mg sine theta here. But you see, I could just as well have written minus mg sine theta if I took up to the plane as the positive direction. The point here is once I write mg sine theta here, whatever direction mg sine theta goes, I have implicitly defined A in that direction as positive. Oh, and then I've got minus mg cosine theta here, right? Yes, sir.
So if we had defined positive as going up the plane, would that mean that the normal force now has to be negative for the perpendicular acceleration to still be zero?
No. I mean, if you could define this way or that way, independent of the perpendicular direction changing. Unless we're also making some sort of like idea about handedness, but I haven't talked about that. I mean, right-handedness, right? Like. Okay, so more to the point then, what's the acceleration? Just take this, right? The acceleration is equal to divide by m, g sine theta. And, oh, by the way, again, to smell the roses, the normal force is in fact not the weight, it's mg cosine theta in this case. Once I add other moving pieces to this example, you cannot assume that these things are still true. All right? What you have to do in each case is just draw the free body diagram, analyze all of the forces involved, and then you say F equals to ma and work it out direction by breaking it down into the pair of perpendicular directions in which you can analyze things. Now, I think more or less this is how Galileo, like the Galilean frames of reference that started it all. Galileo was not, to start with, he didn't want to go against the ancient Greeks. I think he was actually probably fond, from what I've read, of the old way of doing physics, which is basically kind of like modern chemistry. Why do stuff do what they do? I mean, why do the electrons have to form octets? What do they tell you? To make them what? Happy, right? You want the electrons to be happy, and they're happy if they're in these particular patterns, right? I mean, yes, okay, there's underlying physics and stuff you could explain, but the mathematics to really explain that physics is rather involved. Somebody wants to do it. I mean, I want to do it, but most folks don't. Fine, that's their prerogative. But, the old way of doing physics was a lot like that. Things were where they were because that was their natural place, and heavy things fell faster, lighter things fell not as fast, right? You've seen commercials based on this idea, right? When the fat lady gets on the water slide, she's gonna go faster than like the little kid. I mean, it's a rule of advertising still, right? Well, that's the interesting thing, is this shows you that that's not the case for inclined planes with relatively little friction. The acceleration is independent of mass. It just depends on the angle. And at least it's been rumored to me that this is how Galileo figured these things out. He had a little inclined plane, had strings, musical strings laid across it, and then he had balls. You just roll down the thing, and you could hear the spacing of the notes to tell that the larger and smaller balls fell at basically the same acceleration, independent of mass. Yeah.
Maybe like he possibly had like an idea of like
Air friction.
air resistance or anything.
I think at some point they had to realize that a lot of their ideas, their ideas like Aristotle's ideas, were in one way or another attributable to air friction. Yeah, I mean, I think that's probably. It is true. Some of the things that we say from, a non-Newtonian perspective are in one way or another due to friction. That is something we're expecting. Anyway, that's your first example. We'll do more. Sorry, I have gone 2 minutes over, Marissa.